So what I want to do in the first part of this second lecture is to give you I will not give all the details. Same thing as Payles. If you want, I can tell you after this lecture. But I just want to give you the main flavor of how the proof works. And maybe I will give again the statement. So it requires D to be equals to 2. This is very important. D could also be equal to 1, but this would not be a big surprise in this case. It also requires some continuous symmetry, so it will work, for example, for spin n model when n is greater or equal to 2. In particular, this will work for xy, for classical Heisenberg, and so on. And I will illustrate the proof for the xy model, but modulo small adjustments, it would also work for the others. And there are several ways to state their result. One is to say that there is no symmetry. So for any beta positive, there is no symmetry breaking. Another way to state it, which is equivalent basically to the first one, is to say that the law of the spin at 0 under the Gibbs measure mu lambda n beta with a symmetry breaking east along the boundary. So the law of the spin in the middle of the box under this Gibbs measure on the huge piece of Z2 lattice. This law converges in distribution as lambda n goes to the whole Z2 to the uniform measure on the circle. Uniform measure on S1. So that means even though you broke the symmetry of the boundary, in the bulk of the system, when the boundary flies far away, what you see in the middle is just something which is completely symmetric. And yet another way to spot the lack of symmetry breaking is that for every beta, and for every beta positive, and for every infinite volume limit of xy on Z2, so for any subsequential scaling limit of those measures on the whole Z2, the 2-point function between sigma x and sigma y, so this is the same measurement of correlation as the one I used for Ising model, where I stated this theorem by Kaufman and Onzager and Yang. So on the whole Z2 at inverse temperature beta, this will be less than x minus y to some power which depends on beta. In other words, this always decays at least polynomially fast when x and y go far apart. While in the Ising model, this was equivalent to this crazy constant times 1 over x minus y to the 1/4, but this was at beta c, at the critical point. If beta was larger than that, this would have been greater or equal than, say, 1/3 uniformly in the distance between x and y. So this type of symmetry breaking, of high correlation between x and y, never exists for those spin systems, however, how large beta, or whatever beta, inverse temperature. So this is another sign of no symmetry breaking. And the last sign that I want to emphasize is that if mu Z2 beta xy is any infinite volume limit of xy. I think there's temperature beta. So what that means is limit as some subsequence nk goes to infinity of mu lambda nk theta with some boundary condition here. Any such infinite volume limit, then mu xy z2 beta is rotationally invariant. Rotationally invariant. So what does this mean? It means that if I fix theta an angle in 0 to pi, I can define the map R of theta, which goes from 0 to pi to the power z2 with value in 0 to pi to the power z2. Maybe let me call theta 0, and which to a configuration theta I in z2 will assign a new configuration theta I plus theta 0 mod 2 pi I in z2. So this fourth point, what it means is that if I have an infinite volume limit of the xy model, or of the classical Heisenberg model, this would also be true. If I fix one global angle theta 0, and now I have an infinite volume limit of xy, so each point of z, and let's say I sample one configuration according to this infinite volume limit. So maybe I have spins like that. If I want to understand the push forward measure under a rotation by theta 0, so if I want to understand R theta push forward of mu z2 beta, how do I understand the push forward? I sample my infinite volume xy model and I globally rotate all those random angles by the same theta 0. So maybe I do something like this. They are all rotated by the same angle theta 0. I hope you see what I mean. So theta 0 is everywhere here. I get a new field of angle which is rotated by theta 0. This new field of angle is sampled according to this push forward. And what Mermin Wagner tells you is that this measure is the same as the initial one. So whatever you do, whatever way you prepare your system, you get rotational invariance in the infinite volume limit, so you don't break the symmetry. How does the proof work?
Christophe?
Yes.
Sorry, this is a question just because I wasn't listening hard enough. What is this, the second, the fast thing? The second arrow.
Mu fast.
Mu fast. Does that say fast?
Mu fast.
So there's a word that looks a bit like fast.
Oh yes, it's
It's east.
Yes. Yes, sorry.
Okay.
Sorry. Yeah, I know my handwriting is yeah, I know. So don't hesitate if it's not readable. So how to prove this? I will tell you maybe how to prove the second point. Namely, why is the spin just at 0 invariant under rotation? And the extension of this proof to this proof is very easy. I will tell you how you do it. But I will focus on the point in the middle. So proof, so very sketch of proof that sigma 0 in the infinite volume is the uniform measure on S1. So the main step is to build a small energy spin wave. So maybe I will define what I mean by small energy and by a spin wave. So, and then I will, maybe I will motivate why first. So the probability weight let me do it in the angles, of an XY configuration in a box lambda, this is proportional with respect to the uniform measure to exponential beta sum over I next to j cosine theta I minus theta j. Okay, so let me just write the Radon-Nikodym derivative. So this is what we have seen in the first lecture. And what we can argue is that this is close to exponential minus beta over 2 sum over I next to j. And, okay, maybe let me do it like that. So, 1 minus 1/2 theta I minus theta j squared. So I Taylor expanded the cosine, which I would need to justify many things here. This is not quite accurate, especially at a high temperature. But let me Taylor expand. And so this doesn't play any role. This doesn't see the theta configuration. So this is more or less weighted according to exponential minus beta over 2 sum over I next to j theta I minus theta j squared, which for those of you who like the GFF looks a little bit like a 2 pi valued, 0 to pi valued GFF. So the first idea in the proof is to look for fields of angles which minimize this Dirichlet energy, which minimize the sum over edges of the gradient squared of the angles. So a spin wave so I will so a spin wave will be a function psi, which will go from lambda n, which is minus n squared. I will stick to dimension 2 for the moment, with values in 0, 1, which is such that psi at the boundary of my domain is equal to 0, and psi in the middle of my domain will be equal to 1. So that's any function like that. And what will be relevant for us is the Dirichlet energy of psi. So this stands for Dirichlet energy, but since we've seen that my handwriting is bad, Dirichlet energy. And this is defined as the sum over I next to j in this box of psi I minus psi j squared. And a good set of spin waves, so depending on the references, a spin wave may be the best possible such function according to Dirichlet energy. For me, a spin wave is any of those. But a good spin wave because I will want to emphasize in the proof that we don't necessarily need to find the best possible one. A good spin wave is such a function psi with small and possibly vanishing as n goes to infinity, namely as lambda n goes to 2, with small Dirichlet energy. So let me build one for you. And what I will build, it will be slightly easier, is one which is equal to 1 on the boundary and 0 inside. And by 1 minus, you find the one I define. So how do so maybe psi is equal to 1 minus psi tilde, and I will build a psi tilde for you. So what is the first candidate? I think the first candidate we may have in mind to interpolate between 0 and 1 is to go through the L infinity boxes in Z2 and to go linearly from 0 to 1. So maybe at distance n, I want to have 1. And in the middle, at distance I, maybe I try to set I divided by n, and this will slowly go from an angle 0 to an angle 1 by the time I reach distance n. So if I try this psi tilde, what is the Dirichlet energy of psi tilde, which is the same as the Dirichlet energy of psi, of 1 minus psi tilde. This Dirichlet energy is roughly up to constant. I will sum from I equal 1 to n, or maybe 0 to n. How many points do I have on the highest L infinity ball? I have of order I point, maybe 4i, but this will not make any change. And what is the Dirichlet energy which is accumulated around this ball? Those points, they don't accumulate any Dirichlet energy because they are said to be equal. But those points accumulate a little bit of Dirichlet energy. How much? Well, I have I plus 1 divided by n on this layer, and I have I divided by n here. So that's the gradient that I have along each of these edges, and I want to square my Dirichlet energy. The square is really coming from the Taylor expansion of the cosine. If I compute this, so this is 1 over n squared, I will have 1 over n squared, sum from I equals 1 to n of I. So that's not good, right? That's of order 1. And for me, a good spin wave, something which I will be able to use in the rest of the argument, is something which will require a tiny amount of energy so that I can introduce some symmetry in the system. So this first guess is not good, but is there for pedagogical reasons. So let's make a second guess. So this is guess 1. Guess 2 is something which will use the fact that there are many edges here, so maybe it's better to make a small gradient here and to speed up the gradients as we reach the break of the system. So there are many ways to make this second guess less artificial than what I will do, but let me throw out the guess 2. So the guess 2, I will use psi on the L infinity ball at distance I to be 1 plus 1 half plus 1 over I divided by log n. So this is more or less 0 in the middle, and this is more or less 1 by the end of the day when I reach the boundary of my box. What is the Dirichlet energy of psi tilde, which is the same as the one I wanted to, with 0 outside, 1 inside? This Dirichlet energy is sum from I equals 1 to n. I still have I points up to a factor of 4, maybe, along my L infinite box of radius I. But now the Dirichlet energy, the gradient square here is, let me do it slowly, is 1 plus I plus 1 minus 1 plus 1 half plus 1 over I divided by log n, all this square. And this is nothing but, this will be the only computation, I think. Sum from I equals 1 to n of I times, only this one remains. 1 over I plus 1 or 1 over I is more or less the same. So I have this log n squared. And this is much better because I have 1 over log n squared times sum from I equals 1 to n of 1 over I, which itself is a log n. So this computation gives me a Dirichlet energy which is vanishing like 1 over log diameter of the box in which I am working. Okay? So I found a good spin wave because its Dirichlet energy is vanishing as my box is going to infinity. And in fact, it's impossible up to multiplicative constant to do better than that. So I just, because I see some better specialists, way better specialists than me in GFF, which already got guess 3. So guess 3, the best spin wave, the best possible spin wave, namely the argmin of this Dirichlet energy. This is going to be psi tilde best. Maybe let me do psi best. Here, psi is good. Psi best will be the harmonic extension. So, of what? So you have the lambda n box of Z2, and you take the harmonic extension of 0 boundary condition outside. So if you only do this, it's easy to compute this harmonic extension. It's 0, but it's not very interesting. So there is a twist. You put 1 just at that point, and you take the harmonic extension of this function. If you do this, this is something which will slowly move away from 1 and reach 0. And the Dirichlet energy of this harmonic extension is the best possible Dirichlet energy you can do for these constraints that I have here. And if you compute this by random walk estimates, you will also find a better constant divided by log n. Okay, so the step 1 in the proof of Wagner is to be able, for large boxes, to build good enough spin waves like that. Now, what is the second step? So step 2. So imagine that I have my lambda n box, and I have any boundary condition sigma bar. Could be east, could be fast, could be anything. So that's my sigma bar, and I want to convince you that the law that I see here is very close to the uniform measure. So the idea is very nice. It will be to act on this measure a little bit like I did before with this push-forward measure. What I did before to state the theorem is that I fixed an angle theta 0, and globally I rotated all the spins by this angle theta 0. In the second part of the argument, I will do a more subtle, I will use a more subtle way of acting on the system. I will act on the system using my spin wave psi. And maybe even theta 0 times psi. So this function is 0 on the boundary and is exactly theta 0 in the center of my box. How do I act on a... So this is a field of angle, this is theta I in lambda. How do I act on a field of angles in my box with a rotation by a spin wave? Exactly as before, but in a less global way. So now this will be the field of angle theta I plus theta 0 times psi at I. All of this modulo 2 pi, indexed by I in lambda. So let me try to show you on a picture what this would mean. Let me fix any boundary condition, and then in this domain I have the xy measure, which is whatever complicated random field of angles. So this would be better with the slide. And now let me act with this transformation of my state space. What it will do is that very close to the boundary, it will almost not move anything. It will only move things by theta 0 times the value of this spin wave, which is very close to 0 on the boundary.
Theta 0.
What is this?
Yeah.
So what I want to show you is that the law, what I see here is invariant under any shift by any angle theta 0.
Now we fixed the theta 0.
I fixed theta 0.
It's not the spinator actually.
Yeah. Sorry?
It's not the spinator actually.
No, yes, okay, you're right. So this is really bad. So let's call it theta bar. Good point. So for any fixed theta bar, I want to show that my goal is to show that theta 0 plus theta bar has the same law as theta 0. If I show this for any theta bar, maybe even an irrational would be sufficient actually. I guess, but let me not do this. And to show this, I still need to argue in a global way. So I fix this theta bar. I want to shift the spin at 0 by this theta bar, but I will use the whole power of my spin wave everywhere in my domain. And so I will shift things in a very tiny way here, but as I get close to 0, I shift more and more, and when I reach 0, by definition, I exactly shifted by theta bar. I broke 5 of those. Okay. And I would want to say that this new angle that I found has basically the same law as the one I am interested in, to identify that there is rotational symmetry. How to prove this? We will show that this spin wave rotated system is in fact very close to the initial system. So step 3, once I have this action on my state space, I want to show that the total variation between the Gibbs measure in this box and the rotated one are theta bar psi acting on this, the push forward of this under this transformation. This total variation is very small. It's going to 0 as n goes to infinity. If you've never seen that, one way to define total variation is the minimum over all couplings of the probability that, so you want to couple, to find a joint coupling of this probability measure with this one, and you want to minimize the probability that under the joint coupling you have a different output. If you have the same measure, you can use as a joint coupling, you just put the same element on both. If they're a bit different, you cannot do this, but you can try to minimize, and the total variation distance is exactly trying to play this game. So in other words, if you find a vanishing total variation distance, it means you can find somewhere a coupling which produces the same global field of angles for both with high probability. And one is rotated by theta bar in the middle, the other is not, so that's a way to prove rotational symmetry. So step 3 is to try to show that this goes to 0. But for those of you who did maybe mixing times of Markov chains or things like that, you probably know that controlling a total variation distance, which is a L1 type of distance, this is difficult. So we don't do this directly. The step 4, maybe I'm subdividing into too many steps here. But the step 4 is to find another analytical way of comparing probability measures, which is more amenable to statistical physics, and this is called Pinsker inequality. And this tells you that the total variation squared between two measures is less or equal, maybe there is a factor 2, I don't know, but is less or equal to the relative entropy between mu and mu. And relative entropy, I will not define because it's a sketch. I can do it if you want after the talk. But relative entropy is very nice for a Gibbs type measure. Is nice for Gibbs measure. It's basically tuned for those. So it turns out that it's much easier to compute the relative entropy of the rotated measure with respect to the initial one, or vice versa. And it's almost over because this involves the Taylor expansion of the cosine. So it's almost over because the rotation has been built in such a way that there is small Dirichlet energy. But in fact, so the last step is a very nice trick. So the whole game is to compute mu lambda n beta sigma bar minus the rotational one r theta bar psi mu lambda n beta. So it's to upper bound it with the relative entropy of the one we want versus the rotated one. So this, I claim, this is easy to write down what this means, and it's easy to Taylor expand and to analyze. But there is one big problem in this thing, which is that the Taylor expansion of the cosine, we are not manipulating the ground state here. There is energy. The theta I and the theta j, they are not necessarily close to each other. For finite beta, there is fluctuations everywhere. So in fact, when you compute this, you also have in the Taylor expansion, you have the cosine. So what we really need to do, there is the cosine interaction, but we need to Taylor expand around theta I minus theta j, which is not necessarily 0. So there is a sinus term which is here, which is the first order term, and this doesn't go away. So the very nice trick that I think Pfister introduced is that you lose a little bit in the upper bound, but you gain a lot by saying that this total variation squared is less than this relative entropy. But you lose a little bit by symmetrizing the system. So I have r theta bar psi against mu, and I add the other relative entropy versus rotating in the other direction, minus theta bar psi against mu. So both of those are positive. You kind of take the system, you rotate in theta bar and in minus theta bar. You add the two relative entropies, and it kills the Taylor terms of order 1. Only the Taylor terms of order 2 remain, and those are controlled by the Dirichlet energy of psi. And thanks to this, you get that this is less than a constant divided by log n by the step 1 computation. And this means that the total variation is less than 1 over square root of log n, which gives a quantitative rotational invariance of the system in the diameter of the box. So there are many details that are left, but those are really the main steps which avoid me to do some computations on the blackboard. But I'm happy to do those just after.
So how can you do this symmetrization trick?
How can I do?
What is involved in this inequality where you symmetrize the theta bar and minus theta bar?
So the only thing which is involved is that the relative entropy is always a quantity which is positive. So I'm losing something, but I'm allowed to add this relation.
You are adding something which is positive.
Yes. And I have never found a way to avoid this step, but each time I gave this proof with more details, there was a very nice debate that yes, you can use some, but it always collapsed so far. So, but I wanted to avoid the debate and gain some time. But we can debate after. But with all those steps, and this generalizes nicely to the S2 value, the group value, anything you want. And you see that in dimension 2, you never have any symmetry breaking. So let me go to dimension 3 for just a little bit.
Maybe I'm missing some subtlety. Like in the top of step 3, what is this sigma bar meant to know?
No, you don't miss a subtlety. I never quite defined those. So,
okay.
So far, I always defined my probability measure in finite boxes of ZT, and I never quite mentioned what I was doing on the boundary.
Okay.
So for most of what I talked about, there was no boundary. The system was completely symmetric. Only in the simulations, I said at some point, maybe I can break the symmetry with something outside, maybe east or something. If I want to prove Mermin-Wagner's theorem, which is a statement about any possible infinite volume limit, what this sigma bar would be the output of what the system is doing away from that box, which I have no control on. So this could be a pretty complicated configuration. And anything which is inside is interacting with this via those interactions here. And that's because of this that the first Taylor term, you cannot say they go to 0 by some symmetry, because the sigma bar kills all possible symmetry. So if we go to dimension 3, you can ask yourself, can you do the same game? So imagine you now have a 3-dimensional box, and you put east boundary condition on the boundary of this box, and you ask yourself what's going on in the middle of the system. So you then wish to look for a spin wave which would be 0 here and 1 in the middle, and try to minimize the energy cost. You could look at attempt 1, attempt 2, other attempts, but at the end of the day, if you go to the best possible spin wave, it will be the harmonic extension with 0 everywhere on the boundary of this 3-dimensional box. and it will be 1 in the middle of this three-dimensional box. And now, by transients of the random walk, what is the harmonic extension? If you take just the neighboring point here, the simple random walk has a positive probability to not hit this point and go straight to the zero boundary condition. So the harmonic extension here is strictly less than 1, uniformly in the size of the system. So in particular, the Dirichlet energy of the best possible function of this harmonic extension is greater or equal to 6 times this non-vanishing constant. So this is a proof, almost a full proof, that in dimension 3 there does not exist good spin wave which make the Dirichlet energy vanish. So in particular, this whole proof that you can couple the system and the rotated system together in such a way that it's indistinguishable, this proof collapses. And it turns out that in dimension 3 and higher, you recover long-range order, symmetry breaking, and all these things which worked for Ising, but you need dimension 3 and higher. So in the slides, I wanted to tell you, so when should I stop?
We started quite late, right? Maybe in 15 minutes?
Okay. So,
Dimension 3, you have long-range order for large beta,
yes.
but not for small beta.
Right. And in some sense, for all of those systems, if you are S2 valued, for example, you are less correlated than what the Ising is doing. And this is not difficult to show. So because of that, at high temperature, you are less correlated than the Ising, which you know is anyway exponentially decorrelated. So there is no chance that at high temperature you will have symmetry breaking. But what is non-trivial is that at low temperature you break the symmetry. So
Is there also some monotonicity in beta? Like if you look at the two-point function, is it known that it's monotone in beta?
Oh yes, so that's a very good question. So it's known for Ising.
Yeah, because of the propagation connection. So
Right, exactly.
you have some propagation for xy.
For xy, there is a weaker sense of percolation, but there is, but it's not the way to prove what you are telling. It's called G-Libre inequality, what you are telling, what you are asking. And this is true for xy, and it's very useful. For classical Heisenberg, it's not known. And it's a big open problem and because of this lack of monotonicity, that's why it's not clear that you have a uniquely, you have east-oriented or north-oriented, this is not known, because of the lack of this. So it would be extremely nice to have this extension of G-Libre to S2, but this is resisting for 50 years or so. The last 15 last minutes, so I'll go back on my slides. So we've seen all that. I want to just tell you very quickly about dimension 3. I even wanted to make a proof for you, but I will skip, I will do very quickly. Because the main emphasis of the talk is dimension 2 is the BKT. So if dimension D is greater or equal to 3, we've seen here that you cannot hope for a spin wave. And in fact, you recover symmetry breaking as for the Ising model in dimension 2 with this slight change of dimensions. And this was proved by Fröhlich, Simon, and Spencer in '76. And they relied on reflection positivity, which probably will play a role in Anti's lectures in a quite different way. But it's a very beautiful work. But the fact it requires reflection positivity means that if you remove just one edge in this big torus, then the proof collapses. I don't know how to recover the proof if you remove one edge. So it's a bit embarrassing. For xy, that's okay because there is Libre, but for S2 valued, the whole thing collapses. So I wanted to shortly tell you about another way to do things. which we did with Tom Spencer, but I will only, it's a parenthesis, it's d equals 3, so I will only quickly tell you the story, because in the last 5 minutes I want to go back to BKT. And with Tom Spencer, we found another way to detect symmetry breaking in dimension 2 plus epsilon and higher. And it relies on an input from Bayesian statistics, which is due to Amit Singer. And the whole field of research there is called group synchronization. And it was motivated in Amit Singer's work by the following problem. I think they were looking at proteins, and biologists were able to freeze those proteins and then take pictures of those. But what they wanted to do is they wanted to classify the different proteins and recognize those. And so the problem they had is that at the moment the protein is frozen, they don't know in which orientation the protein is frozen. So they had to put the same proteins on the same orientations. So they had to mod out the SO3 symmetry. And the protein has some thermal fluctuations, so there is a bit of noise that makes the synchronization more difficult. So they designed a whole theory of synchronizing things up to noise. And later on, in 2017, Abe, Massoulier, Montanari, Srivastava, and Sly, they wrote a paper called Group Synchronization on Grid. And I really liked the title, so I looked what it was. And later on, with Avelio, we did the work which was that had a similar flavor to this group synchronization. And we added the reference in the paper just because there was some similar flavor. And Tom Spencer spotted this reference and asked what it was about. And then we reinterpreted this work in terms of statistical physics. I will go back to it in a second. Well, maybe I won't. So, okay, maybe I will quickly tell you group synchronization. So the setup is as follows. You have a grid, the same grid as the one I have in this course. But now each point each vertex carries a group element. So this is why I was happy to answer a question by you, I think, earlier on. So each point x carries a group element which I call ux and which is gx here, which is in a Lie group. And out of this field of Lie group elements, you build data which along each edge tell you what is the increment in this Lie group along that edge. And the increment is gi minus 1 times gj. So on each edge you say how you go from this group element to the other group element. And since it's Bayesian statistics, this data will be corrupted in the sense that along each edge you know how you go from one group element to the other, but you add a little bit of noise. So the whole system is a bit noised by some IID noise. And now you ask the question, given two distant points x and y, given the local increments, the noisy local increments, are you able to predict with good accuracy what's the increment from x to y? What is gx inverse times gy? And they prove this phase transition. They say that if the dimension d is 3 or higher, then if the noise is large, it's impossible to recover, whatever estimator you use. But if the noise is small enough, then yes, you can recover up to good accuracy what is the orientation between x and y. And the statistical estimator is using a very nice theorem of Benjamini, Pimentel, and Perez, which is called the unpredictable path theorem. But I won't go into it. And with Tom Spencer, the same Tom Spencer as the Fröhlich-Simon-Spencer, we could find a new proof of symmetry breaking, but in the presence of some quench disorder. So on the one hand, it's nice to have a quench disorder because in principle it makes symmetry breaking even harder. But we were not able to project our result back to the pure system. until Jörg Fröhlich, the same Fröhlich as Fröhlich Simon Spencer, told us that, by the way, if your system is xy, is S1 valued, there is a less famous Génibre type of inequality which allows us to project our result back to the pure system. So in the end, it's just a tiny remark where we thank Jörg Fröhlich, but since then, this is what people enjoyed the most in this work, this remark, because it now gives us, at least for xy, a completely new proof of symmetry breaking, a proof which works on any graph which has sufficiently non-self-crossing paths. So for those who do group theory or where this property is useful, any graph which has the exponential intersection tail has symmetry breaking for xy at low enough temperature by this new proof. So that's all what I wanted to say in dimension 3 and higher. And I have 5 minutes left to go back to dimension 2. So in dimension 2, so I will start telling you about the Berezinskii-Kosterlitz-Thouless transition. So this is Berezinskii, this is Thouless. And they were awarded the Nobel Prize in 2016 for the discovery of topological phase transitions. And xy in dimension 2 is the archetypal case of a topological phase transition. So the way it goes is that I told you about this Mermin-Wagner theorem, which said that there is no symmetry breaking for xy or classical Heisenberg or any of these spin systems on Z2. And I watched Kosterlitz Nobel Prize lecture, and at some point he gives a very nice anecdote. He says that he got a postdoc in UK, he didn't quite want to go to UK, wanted to go to Italy, I think. But still he went to UK and he worked with Thouless, and Thouless tells him it's very strange because there is a mathematical theorem by Mermin and Wagner, and on the other hand, the experiments with liquid 2D helium seem to show some strange behavior of the free energy. So how come the experiment shows something and there is a mathematical theorem which tells you there is nothing to see? So they spent some time trying to understand things, and they managed to find a more subtle phase transition than what was previously known. So they found a phase transition which didn't go against the mathematical theorem. Fortunately, there was no mistake there. But what they spotted is that if you take the xy model, at large enough temperature, the 2-point function decays exponentially quickly. So the cosine theta x minus theta y, the average of this decays exponentially quickly in x minus y. This is very easy to show if t is large enough. But what they predicted is that if t is small enough, you turn to a different phase where it now goes polynomially, it's polynomially slow, the decay. And in this summer school, where there are at least 2 courses about conformal field theory and things like that, I think you like those exponents, you like those power law decay. This is a sign of scaling limits and everything. So I guess that's why I'm here today. So the system is transiting from maybe a boring phase of exponential decay to a more interesting phase where you have polynomial decay. But the difference with Ising is that you have a whole line of CFT, potentially, a whole line of points where you have critical exponents. And another very peculiar part of this transition is that the free energy is analytic here, analytic there. So analytic there is there is no dot. Analytic there is a slight dot. It could be a slight dot. But there it's believed to be C infinity. So I still don't know how Thouless spotted anything on the free energy because it's a C infinity curve. Analytic both sides C infinity at T, and he spotted something weird at the BKT temperature. So very good eyes. But it's an example of an infinite, what's the name? The phase transition of infinite degree, I think. Order, thank you. Order, infinite order. Okay, so next, okay, last slide. So we've seen Ising model. There is symmetry breaking at low temperature, exponential decay here, and this is where the SLE3 of Maurice's lectures stands. That's easy to spot exponential decay at high temperature, and my goal in these lectures will be to justify to you that you transit to algebraic decay. So this will be Thursday. There is a phase transition of a new nature here. And my favorite conjecture of all is that if the symmetry group is continuous and non-Abelian, it's supposed to be exponential decay at all temperatures. So this is a prediction due to Polyakov in 75. So if you have S2 valued spin system, it's conjectured that whatever beta is, it's always exponentially decaying. So you may say this is maybe a boring system like Ising model in dimension 1. But let me tell you, this is not boring at all, because the proof of this would be a toy model for the confinement property of Young Mills in dimension 4, related to Mylin's lectures. So next time I will focus on this part of the phase diagram to try to show why there is algebraic decay at low temperature. Thank you.